When you stop and look around, it's kind of crazy how many things in our world just move back and forth. I mean, think about it, a skyscraper swaying in the wind, a bee's wings buzzing. There's this hidden physical principle, like a secret code, that governs this whole endless dance. So let's dive right in and unpack one of the most fundamental rhythms in the entire universe. All right, so let's start this off with a bit of a puzzle. On the surface, these things seem completely different, right? I mean, a grandfather clock, a guitar at a rock concert, even a solid block of salt. What in the world could possibly connect all of these? The answer is they all oscillate. It's a fancy word, but it just means they move back and forth around some central, stable position. But here's what's truly amazing. It's not just that they move, it's how they move. They're all following a very specific, very predictable pattern. It's like a universal blueprint that we are about to decode. Now, to get a grip on this huge, universal rule, we've got to simplify things. We're going to crack the code by looking at the most classic textbook example of an oscillator you can find, just a simple mass attached to a spring. Believe it or not, this little system holds the key to everything. Okay, so every good story needs a hero, right? And in the story of oscillation, our hero is the restoring force. And it's a beautifully simple idea. No matter where you move the object, this force is always trying to pull it back to where it started, its stable equilibrium position. It's like a constant voice saying, hey, get back to the center. And here's the deal. This force doesn't just do whatever it wants. Nope, it follows a really precise rule, and it's called Hooke's law. Now, don't let the equation scare you. It's super simple. F equals minus kx. F, well, that's our restoring force. X is just the displacement, how far you've pulled the object from its comfy center spot. And K is what we call the spring constant, which is just a fancy way of saying how stiff the spring is. But really, it all boils down to this. The farther you stretch it, the harder it's going to pull back. That's it. Now, I really want you to pay attention to that tiny little minus sign in the equation. It might seem small, but it is without a doubt the most important part. It tells us that the force is always pointed in the opposite direction of the displacement. So if you pull the mass to the right, the force yanks it to the left. You push it to the left, the force shoves it back to the right. It's always trying to get back home to the center. Okay, so we've got the rule for the force down, but what kind of motion, what kind of dance, if you will, does this very specific force actually create? Let's translate this rule of force into the actual language of movement. So here it is, our simplified model. We've got a mass, a spring, and, this is crucial, a frictionless surface. In our perfect little world, that means nothing's going to slow it down. So we pull the mass to one side, we let it go, and now let's actually map out the precise dance this thing creates. And this is what that dance looks like when you plot it out over time. You see these beautiful, smooth waves? They represent the object's position, its velocity, and its acceleration. Just notice how they're all oscillating, but they're kind of out of sync with each other. They're all related, for sure, but they each hit their peak at totally different times. Let's break that rhythm down. So here's the heart of it. When that mass is at the very, very end of its path, its displacement is maxed out. It has to stop for a split second to turn around, so its velocity is zero. But because that spring is stretched to its absolute limit, the restoring force is at its maximum, which means its acceleration is also at a maximum, yanking it back the other way. And then as it zips through the center, it's moving its fastest, max velocity. But for that brief instant, the spring isn't stretched at all, so the force and acceleration are both zero. Right, but think about it. On a surface with no friction, a system like this could just go back and forth forever. So what's its power source? Where is the energy coming from to keep this endless dance going? Let's really dig into this from an energy perspective. What's actually fueling this motion? Okay, so at the absolute edges of the swing, the mass stops dead for a fraction of a second. At that moment, its kinetic energy, the energy of motion, is zero. All the energy in the system is now stored in that stretched or compressed spring. We call that potential energy. It's just stored up energy, ready and waiting to be released. Think of it like a pulled back slingshot. And then, as that mass comes flying through the center point, the spring is totally relaxed. That stored potential energy just dropped to zero, because all of it, every last bit, has been converted into the energy of motion, kinetic energy. And that's exactly why the mass is moving at its absolute fastest right at that point. And here is the big, beautiful reveal. The total energy of the whole system, it never, ever changes. It's constant. It just gets endlessly transformed, sloshing back and forth between potential energy in the spring and kinetic energy in the moving mass. It's this perfect closed loop of energy swapping. Okay, we've done it. We've gathered all the clues. We have a very special kind of force, we have a specific pattern of motion, and we have this constant trade-off of energy. So it is time to put all the pieces together and give this whole phenomenon its proper name. This hidden rhythm has a name: simple harmonic motion, or just SHM for short. That's the official blueprint. And it's not just any kind of back and forth motion. It is specifically the kind that happens when that restoring force is directly proportional to the displacement. That really simple rule, Hooke's law, that we started this whole thing with. So at the end of the day, this is the ultimate takeaway. For any system out there to be in perfect simple harmonic motion, it just needs two things. One, it needs a restoring force that's always trying to pull it back to a center point. And two, that force has to get stronger in a really predictable way the farther the object gets from that center. That's the whole secret. And here's what's just absolutely mind-blowing. This isn't just about some block on a spring in a physics lab. This exact blueprint describes the vibrations in the air that create sound, the oscillations of electric and magnetic fields that we see as light, and the way waves travel across the ocean. This simple back and forth dance is literally everywhere. So the question to leave you with is, what else in our universe is out there dancing